Hello guys, welcome on Tesla Eduventures. In this video, we are going to discuss the gas laws, and we know that there are majorly three gas laws, and the first one of them is Boyle's law. So according to Boyle's law, for a constant temperature, the pressure of a given mass of a gas is inversely proportional to the volume of the gas, and this can be proved by the ideal gas equation itself. And you know that according to ideal gas equation, PV is equal to nRT, and if T is constant, then the pressure of the gas is inversely proportional to the volume of the gas. And you can also say that at constant temperature, P1 V1 for that gas is equal to P2 V2 for that same gas. So if you will plot the graph between P and V, then you can see that this graph would be a hyperbola. So this would be the hyperbolic graph, and if you change the temperature and you again plot this graph, then this graph would be different. So there are three graphs which are plotted for three different temperatures, and you can see that for same pressure the volume of these three graphs is different, and the graph which has the greatest volume at the temperature P1 will have the greatest temperature. Obviously at the pressure P1 will have the greatest temperature. So we know that if V3 is highest, then obviously T3 would be highest. So this would be the sequence of temperature. And if we plot the graph between log P and log V, then this graph would be a straight line going in the downward direction. This can be proved by taking log. So ln of PV is equal to log of constant, which is C, and this is ln P plus ln V is equal to C. So ln P will be equal to C minus ln V. So ln V is minus X, and this is y, so y is equal to C minus X. So this is a straight line which is going in the downward direction, and this curve is also called as isotherm due to the fact that the temperature is constant on this curve, and the constant temperature process is called as isothermal process. So this curve is also called as isotherm. Now let us move on the Charles law. Now you must have heard about the Charles law, that at constant pressure the volume occupied by a fixed quantity of a gas is directly proportional to the absolute temperature of the gas. Now by the term absolute temperature, we know that it is the temperature in Kelvin. So we can see that PV is equal to nRT, and if P is constant, then volume is directly proportional to temperature. So V is directly proportional to T, and V by T is constant. This graph would be a straight line which could pass through origin, but we would not draw this line till origin because the absolute temperature 0 degrees Celsius cannot be achieved. So we would not touch this graph on the origin, and you must have heard this Charles law already. But let me tell you the different form of Charles law. This is the Charles law in degree Celsius scale. So now let us see, we will analyze the definition in later on. Let us analyze the Charles law in degree Celsius. So we know that at 0 degree Celsius, which is 273 Kelvin, V is equal to V naught, let's suppose. And at T degree Celsius, which is T plus 273 Kelvin, the volume is equal to V. So we know that we could apply this a formula for absolute scale only. So V naught by temperature in absolute scale is equal to V by temperature in absolute scale. So V naught by 273 is equal to V by T plus 273. And V is equal to V naught 1 plus T by 273, where T is the temperature in degrees Celsius. So you can see that what this Charles law in degree Celsius states, that at constant pressure the volume occupied by a fixed quantity of an ideal gas increases by V naught by 273 for each 1 degree rise in the temperature, where V naught is the volume at 0 degrees Celsius. What I am saying, that If at 0 degree Celsius T is 0, then V is equal to V naught. At 1 degree Celsius, V will be equal to V naught plus V naught by 273. So change in volume is V naught by 273. At 2 degree Celsius, V will be equal to V naught plus 2 V naught by 273. Now again the change in volume is V naught by 273. So for each 1 degree rise in temperature, the volume increases by V naught by 273, where V naught is the volume at 0 degree Celsius. So this graph would be a straight line going through this point and this point, and this would be obviously minus 273 degrees Celsius, because at minus 273 degrees Celsius, which is 0 Kelvin, the volume will become 0. Volume will cease. Okay, so this is the Charles law. This graph is not being plotted in the second quadrant. It is started from this axis only. But let us assume that if it would be going in the second quadrant and it would be touching the x-axis somewhere, then this would be that point where it would cross the x-axis. Now the similar law is Gay-Lussac law, and you also know this law, that at constant volume the pressure of a fixed quantity of an ideal gas is directly proportional to the absolute temperature of the gas. Now what does it means? It means that if by PV is equal to nRT, we can see that if V is constant, then P is proportional to T, and similarly the Charles law, we can say that P by T is constant. Now again the graph between P and T would be the straight line, but again this straight line would not be passing through the origin. It is due to the fact that the absolute temperature could not be 0. Okay. Now in degree Celsius scale, again we can say that Gay-Lussac law in degree Celsius is P is equal to P naught 1 plus T by 273. So what we can say, that for each 1 degree rise in temperature, the pressure of an ideal gas at constant volume rises by P naught by 273, where P naught is its pressure at 0 degree Celsius. So again the graph between pressure and the temperature in degree Celsius would be like that. So this is the Gay-Lussac law in degree Celsius scale. So these three laws were the gas laws which gas obeys, and in the next video I'll be bringing the degrees of freedom of the gases and monatomic, diatomic, triatomic gases. Thank you.